I just want the screen for the beginning.
Okay, so all three of these lights off? Yeah.
Yes, I think I got it.
Looks like you got it.
Should we put them over there? Because everyone's used to having them over there.
Yes. Wherever they usually are.
They're usually here.
Got the calendar there. Hey, good morning. Good to see you. For you.
Hi, Lanta.
Thank you for.
It's fun. No, the students are fantastic. It's been really a lot of fun. Did you just arrive?
I just arrived last night.
I think your has been floating around.
Here.
Ah, you got it. Oh, you're making it better.
Yeah, hopefully.
I'm really just showing you a couple slides and then we'll go back to.
I'm just making sure the microphone is.
Fantastic. Yeah, we might be slightly low this morning since there was the barbecue and I heard there was a drinking off. No.
It's just 9. Should we go ahead?
Yeah, sure.
Good morning, everyone. So just a reminder, for Heather's talks, we're asking people to unmask up. There are masks up here. You don't have one. And yeah, this is Heather's final talk on the LHC experiments.
Yep. Good morning, everybody, and well done for everyone who made it here after the barbecue last night. I appreciate it to do it. All right, so let's get started. So one thing I wanted to start with is going to be a movie here, okay? And what it's going to try and show you is kind of put together all the things we've been talking about, tracking detectors and calorimeters and things like that, to sort of move towards how we're actually going to identify particles. And so the lecture today is going to have 2 parts. I'm going to tell you a little bit about the algorithms that we use to find particles. And then I'm going to finish up by sort of bringing it together using examples from physics analysis. Okay? So we've gone all the way from accelerator through detector to physics analysis, which gets a bit closer to the stuff you guys are normally thinking about on the theoretical side. Okay.
Particles.
Uh-oh, hold on. I hate the sound of this thing. Uh-oh, that's not what we want. We will come back to that one in a bit. Let's turn off sound. Okay, let's try that again without sound. Okay, so what you want to watch is you want to watch the various different particles that are getting produced at the collision. We're looking sort of transversely through the detector. And the first one here, that was an electron, and then a photon. Oh, I can't pause. Okay. We'll just let it play, and then I'll talk about it afterwards. But what you want to pay attention to is what's happening in the various different detector layers. So here's our tracking detector. Here are the calorimeters, and way out there are our muon spectrometers. You can see, for example, the difference in the showers that we were talking about for the hadrons versus the EM particles. And now we're going to have a muon, which goes all the way through the detector, does almost nothing, and interacts a bit in the muon detectors. Neutrino, we can't really see much. Yep, question.
What's the muon detector made of that allows the muons to interact?
So it's essentially just a tracking detector. And remember we were talking about like gaseous versus silicon? The muon detectors are typically gaseous detectors that we have, and just loads of material. I mean, the thing is muons do interact. You just need to have a ton of material to actually see it.
Gotcha. And is the readout photons?
No, just different electrical signals. So it's like ionization. like back to the tracking one more than the calorimeter, which was all about that. Yeah.
That's, since the photons are seemingly completely stopping, this is not a sample.
It's a sampling one because remember the stopping was about the depth, right? Did we have enough material to contain the shower in it? Actually, I don't show you anything. This is actually Atlas, by the way. And so this actually would be a sampling calorimeter. You can't really, we're not showing you the readout and things like that. So I have a question. Based on this picture, how are you going to tell an electron and a photon apart? If you're an experimentalist, and this picture is essentially what you got. Yeah. Exactly. So in both cases, you get energy in the calorimeter. Looks pretty similar, actually. But for the electron, because it's charged, we have the track and the tracking detector to do it. Yeah, question?
Why don't the photons interact much in the decal? Is it just too shallow?
Just too shallow. So this is a little bit of a sketch, obviously. There is some interaction that they will have. And also, by the way, occasionally muons would actually leave some energy too. So it's a little bit simplified. But essentially, the majority of the energy needs to be in the hadronic calorimeter, which has much more material.
What's the solenoid in charge of here? Is it still doing some beam direction?
Nope. The solenoid, which is here, it is bending the charged particles in the tracking detector so that we can measure the momentum. We actually also have, which is not drawn here, there are magnets in the muon spectrometer as well, which you need to bend the muons so we can measure their curvature. Yeah?
Did you have 100 of them happening at the same time?
We don't have 100 yet, 40, but.
More than one event happening at the same time. How do you figure out which electron and photon came together in the same event?
Yeah, so the thing is, at the moment the average is 40, okay? However, most of the, per bunch crossing, average about 40. At high Lumi LHC, it'll be above 100. However, most of the time, there's only one interesting process. The extra ones are typically soft particles that get produced to do it, and so they wouldn't usually have electrons and things like that in them. They just have tracks. So you typically get a whole bunch of extra tracks to do it. What we're actually going to do, and this is something I'm going to talk about in just a second, is you can actually reconstruct where those tracks came from, like physically, and you can see that they came from a different collision point to the main event that you're interested in. And so we do that. We apply cuts to try and get rid of them as much as possible to do it. And you could do the same thing for an electron in the very rare instance when you'd get that from a pilot event as well.
So can you reconstruct from the hydronized part also after the vortex?
All the tracks we can. So anything that's charged. If it's neutral, we only have very coarse pointing that we can use, and that's more tricky. We can do it to some extent, but it's difficult. Yeah.
I guess I have two, so last one, I guess last one, but is the simple one is there a certain timing resolution to this whole thing?
Very coarse.
Very coarse.
Yeah. What we do have, and something I had to leave out of the lectures, is we have the trigger, okay? And so we have a whole extra set of detectors that decide very quickly if a bunch crossing is interesting. In that case, we read out the detectors. So we don't read them out every single time there's a collision at all. So we know more or less what fits in that event to do it. But timing is not something we have particularly much information about. Yeah?
Thanks. How is muon curvature measured?
We're going to get to that in a second. Yeah.
Could you maybe somewhere in the setup speak a bit to B-tagging?
That's also coming.
Awesome.
All right, I think that sounds like it's time for me to move on, since you're asking all the questions about what I'm going to talk about. All right, I've got to make this all go up. There we go. All righty. So that was just trying to show you, oh, I left some light off, didn't I? Dangerous. That means everyone will go to sleep. Huh. I'm not sure why that happened. I need some help here. Okay, good. Clearly too complicated for experimental physicists.
Is that good? Yeah.
I feel like experimentalists are the ones who should be
Yeah.
That was why I was making the comment. I'm always amused when my theory friends help me to fix electronics that are broken. All right, so step one, we're going to talk a little bit about how we actually find those tracks that we've talked about a whole bunch. So what you've seen is we have a large array of tracking detectors. Arranged in layers. And that was what you were seeing. And sometimes you may have heard that we call it like an onion, the detector. It's not because it smells or something. It's because of the layers that we have to do it.
What does the LHC smell like?
Dusty.
Okay.
Yeah, kind of like a dusty lab. But you can't go in it when it's on. It's too much radiation. All right. And so this is very much a sketch because normally the number of layers is something like 8 to 10, okay? But just imagine that there are a whole bunch more to do it. And what we're after is to record the trajectory of a charge particle. And not just one. In fact, we really want to get the trajectory of all the different charge particles that we have in the event, including all those pileup tracks we've been talking about. And so what happens when we produce our charge particle, it will move through the detector, undergoing ionization in most of the layers that we have to do it. And so what we get is known as a series of space point measurements. And by the way, I'm drawing this in 2D for convenience. This is truly a 3D measurement. So you want to think about that as a whole long cylinder. And we're looking for them in 3D. Yeah?
I'm a little confused about the coarseness of the timing on this. So I would think that you'd want to see when it registered here, when it registered here, and stuff, and so on and so forth, just to kind of have an idea of how fast it's moving. How boost.
It's all too fast.
Okay.
So these particles are effectively moving at the speed of light.
Okay.
To do it. We do have timing information. We read out a detector in fixed timing intervals to do it, but integrate of them. But to see the structure of the timing is super, super fast to do it. These are very small, like the size of a pixel detector, which would be the innermost one, is about this big.
So it's only through deflections that you can kind of make
We get what we need, and that's what I'm going to show you. Yeah.
Is there particle identification in the gases?
Limited. So we talked a bit about this. What's actually going on inside those dots is ionization energy loss, right? And we read out that DE/dx. And you can partially use that to do some particle ID, but it's not particularly strong. It's not designed that way. And so what we want to do with these space points is we want to do something that's what your 5-year-old niece or nephew might do, which would be connect the dots and fit the track.
Is there a template you fit to?
We'll get to that. And so it's really about deciding which of the dots you want to join up, right? Joining them up to do it. And then what we're interested in getting is the momentum and also the charge. The charge is actually pretty simple, right? We know which way our magnetic field is going, and simply does it bend that way or does it bend the other way to do it. But you still want to know that. In fact, we do a little bit more. What we actually do is we determine the locally helicoidal, it's a helix, trajectory using a chi-squared fit. To do it. So effectively what we have is we have 5 different parameters that describe the track. I'll get to you in a sec. About the, where it originates from, its momentum, which angles it's going at. You have the space points, and then you do a chi-squared fit, which minimizes the difference over those 5 track parameters. Yeah?
Are you also recording the time at which you hit each layer?
No. What we do is we read out in a specific time window, those layers, but we don't use the time here. You could do it. And so you don't need to know the time to know the momentum. In fact, the way you get the momentum is simply from the curvature of the track. If you know the curvature, you know the momentum. And indeed, essentially what it is the curvier the track, that would be the low momentum. And if you have a much straighter track, something like that would be a high PT track. And effectively, it infinitely gets straight. And you become progressively worse at measuring as the momentum goes up. Yeah?
What if there are so many points around? Like if there are so many particles moving on?
Why do we have so many layers?
No, I'm saying if we have so many particles leaving a track, how do we know which points to connect?
Ha-ha! That's the hard bit. That's entirely the hard bit because, right, sort of typically we're talking about could be up to 1,000 tracks per event. So the sketch I'm showing you is way simpler than it is. And so this is known as the pattern recognition. And that's the entire challenge of tracking. The fitting's easy bit. The hard bit is deciding which points that we actually use. And to do that, pretty much all the modern approaches use the Kalman filter. Anyone heard of a Kalman filter? A few nods. Kalman filter is super old. It was made up by a guy, oddly enough, called Kalman, but in the 1960s. And it's used for various different things, like for tracking missiles, for doing anything when you want to think about something propagating and trying to figure out its trajectory. And what's kind of smart about it is it effectively steps through the different layers, comparing what we know to what information we have, also taking into account that our particle might be interacting in the material, getting deflected. Remember all those processes we talked about? That all gets built in. And so that's effectively how we do it to get there. Yeah?
How are the uncertainties in the Kalman filter comparing to, let's say, neural network approaches?
So when you get these 5 track parameters, you also get the covariance matrix. So you get the full uncertainties and the correlations. Between it comes out of the formalism. People have tried using machine learning for this. So far, it doesn't do as well. So typically, for tracking, we actually need super high efficiency. So if a particle goes all the way through, nothing goes wrong for it, we typically would get something like 99% efficiency, take rate 10 to the minus 3 to 10 to the minus 5 to do it. And a typical machine learning approach has got to say 90%, not to 99. It's because there's this Kalman filter, which I've only described very briefly, has a lot of the physics built into it, and that's actually important. You had a question?
Yeah, so is the trigger only looking at this tracking information, or is it looking at information from the other detectors?
So we do not have a tracking trigger. So we don't look at that at all. Okay. So one of the interesting problems that means is that we can only trigger on events that we're sensitive to. And for us, that means high PT muons, high PT electrons, or jets, which we'll talk about in a second. We can't trigger on tracks. For the upgrade, CMS is going to have a track trigger. Atlas will not. And so they will be able to trigger on tracks with that. Was there one? No. Okay. Now we want to do, sorry, we're going to do one more computer thing. Because this goes a bit to your question about how hard is it. You're all going to have to do some track reconstruction by eye. Hold on, I need to. Okay. So, here's an event, okay? Yep. And in this event, we're looking for one 50 GV track in it. Now remember I've been talking about curvature? 50 GV track is going to be pretty straight. So all the curvy things you're seeing, not going to be the 50 GV track. And this event has one 50 GV track. Okay, tell me when everyone's more or less done. Okay? Woohoo! I'm an awesome teacher. No, just kidding. To do it. But it illustrates a little bit, how tricky it is and how there's all these different hits and you can easily have confusion in your algorithms to do it. And I think that's actually pile up of something like 1 or 2. Yeah. Oh, sorry, wait. I didn't hear.
By eye, can you do like as good or better than the Solomon question?
No, not even remotely close. For like one track, like we just did, indeed, yes. But when they start to be 1,000, you can't. And secondly, it's all 3D. So to actually visualize properly in 3D, right, is difficult to do it. You can detect like crazy tracks very easily by eye. That way you do better than machine. Yeah, go ahead.
This tracking analysis, this is done directly by some group, and then kind of does the CMS report the data sets to then the real analysis group? Or if I want to do some analysis, do I have to do this myself every time?
So what we actually do is we have something called reconstruction, where we take the raw detector output, including tracking, including jets, which I'm going to talk about in a sec. We run that, and then we produce a format that's designed for everyone to use for analysis. However, if you have like some more complicated analysis you want to do, like, I don't know, displaced tracks or things like that, then you have to go repeat the step. So there's sort of a general processing that's designed for everyone, but you can also do it yourself when you need to do it. It takes a long time. So like to reprocess the data, let's say we change the algorithms, it's like 2 months or so of full-time running on the grid to do it. So it sort of shows you that it's pretty important not to get the stuff wrong because it costs you tons of time. Yeah. No. So we collide 40 million times a second to do it. And so that's way too fast for the clearing. However, we only trigger at a much smaller fraction of that. So typically for the tracking detectors, the rate at which we trigger, the detector is completely cleared. For the calorimeters, on the other hand, there can be a little bit of what's called out-of-time pileup, which is energy left over. But you can correct for this on average. It's not a big effect. Okay, so that was tracking. And now the next one I want to talk about is vertexing. Okay. And so what we're trying to do here is we take our tracks, which we've reconstructed, thank you. And we use them to determine the origin of the physical process. And so now you want to stop thinking about the hits, right? You want to start thinking about the tracks. And you can imagine, right, that we have a bunch of tracks like this. We have some other tracks look like that, another track looking like that. You could imagine, and actually I'm making them stop, which is a little bit misleading, in fact. They would keep going. Tracks just keep going as far as we want. What you could imagine doing is looking through this full collection that you have and asking the question, are there groups of tracks that seem to come from a common point to do it? And that's basically the idea of what we're trying to do in vertexing to do it. Yeah?
Is there an overlap rate, like a chance that you just get unlucky?
Of course. So with vertexing, right, there would be the efficiency, like we were talking about. There'd also be a fake rate. And you can also have weird stuff where you get a split vertex, where like half the tracks go into one vertex, half the tracks go into the other vertex and things like that. And as pileup gets worse, as you get more tracks, you start making more and more mistakes to do it. And so what a vertex is multiple tracks intersect in space. Now, a little bit different to thinking again about tracks. The typical displacements, particularly of what we call the primary vertex, which I'll come to in a sec, are really quite small compared to the sensitive elements. What I mean by that, right, is that your sensitive elements are the pieces in each of the different layers of the detector where you can record information. But the distance between the vertices are typically way smaller than that. So it's not like, there'd be one in one pixel, one in another pixel like that. They're much closer than that. So you need to do more sophisticated things. And what it means is that when we think back to our detector design, we really need precise as possible, effectively, measurements near the interaction point. So if you think back to the lecture on Tuesday when we were talking about the different types of tracking detectors that we can have, that's why we use these pixel detectors, so the ones with the little squares. That's why we put them really close to the interaction point, because we need to have this measurement to be as precise as possible. They're more expensive, they make more silicon, and so you need to use them sparingly, but that's why they would be typically your innermost layers to be able to do precisely this. Questions? Yeah?
I would expect that if you go further, these tracks get further and further from each other, so then it might be better to measure them in distance.
So that's why you also want to make your tracker as big as possible, right? Because indeed, as they're bending, right, they're getting further apart, and so it becomes easier to get the measurement. However, the distance that you extrapolate a measurement over, that also gives you the size of the uncertainty, and so that's why you need those precise measurements close by. You need a long measurement, but it can be less precise further out, but you want it to be as long as possible, effectively. That will improve your momentum to do it. Okay. So then we have actually two types of vertices. we have the primary vertex. And this is really the interaction points where the proton-proton collision occurred. So in an ideal world, you just have one primary vertex, but of course you can get a primary vertex for each pileup interaction, so there are more. Yeah?
How spread out do primary vertices get along the beam? Do you get down to like really one point, or do they just spread out?
Yeah, so in fact the beam has a size, right, like we were talking about. And so what you actually get is you get a beam spot. And so it's pretty small in X and Y. In Z, along the direction, it's a lot bigger. And so the primary vertices are typically on a line, effectively along that, to do it. It's enough that we can typically resolve them all. So they're not so clustered that we can't. But of course, when you're designing your detector, you take that into account to say, you know, what separation do we need to be able to resolve? Occasionally goes wrong, of course.
How big is the spread out?
No, much smaller than that. But I'm forgetting my units. It's 90 something, but I need to double check the units, which would make it a lot more helpful to do it. Yeah, I can't remember. I'll have to check for you. But it's centimeters or smaller. It's not meters at all. And it's something they can control actually quite a bit in the LHC. Oh, sorry. Thanks.
I was curious, so you said you wanted the trackers to be like as long as possible. I was curious how long they actually are, or I guess.
Do you mean long or wide?
Yes.
Radius. Yeah, so sorry, I have this coordinate system in mind, which I probably haven't communicated, is that the beam is here, right? This is Z, and then we have X and Y, which are perpendicular to do it. So a pixel detector, typically that's the diameter actually for the pixel detector. Then they get bigger, sort of a meter-ish type thing to do it. The problem is that silicon is expensive and heavy. So if you make a super gigantic tracker, you will mess up your energy resolution in the calorimeter to do it. And so that's a little bit the balance that you do. So usually sort of meter and a half type scale would be for them. All right, type 2, secondary vertex. This one is the decay position of so-called long-lived hadrons. And primarily what we're thinking about this is we're thinking about B quarks and C quarks. But it also works pretty well for, whatever exotic signature you're thinking about to do it. So let me draw another little sketch about how this could look. So here we have our primary vertex, okay? And we have a bunch of tracks. Oh, interesting track. Not meant to be dotted. Kind of coming out from it. But we have one track here that decays at a secondary vertex. And so this would be our primary vertex. This would be our secondary vertex. And it's the same idea as the primary vertex. What you want to do, right, is you want to look at your collection of tracks, want to cluster them in space, and to ask a question, is there a point which is consistent that a number of these tracks originate from? And this is how you would actually find a secondary vertex. Yeah?
If you have, say, like several overlapping resonances, are in terms of the hadrons themselves?
You mean in terms of the masses? Okay.
Are you able to actually distinguish with decent accuracy which one it is?
Depends on the spacing.
Okay.
And so, for example, like for Atlas, we're not very good at distinguishing between the 3 upsilons. Those end up being a merged mass peak. And that's because we have a lower magnetic field, that solenoid we were looking at, than CMS. It's a factor of 2 lower to do it.
What are the scales on those magnetic fields?
2 Tesla, 4 Tesla.
Okay.
Yeah, and so remember, like the LHC magnets are 8 Tesla. That's getting towards, the edge of what one can do on a large scale to do it. And so when CMS was built, their magnet, they weren't actually sure that they were going to be able to build this 4 Tesla magnet. And so that's why Atlas design was done differently in case the magnet didn't work. Yeah?
Are the innermost tracking detectors in close enough that some free quarks make it to the detector?
Yeah. So this secondary vertex for Atlas quite often flies through the first layer. And you can actually look at that energy. If it's charged, you can look at the energy it deposits. There are also, for example, like Targino searches, which look for charginos that go some distance in the detector and then decay and go on. If it's neutral, you don't see it to do it. Okay, so that was tracking and vertices. The next one I want to talk about is something I keep mentioning, but haven't really spoken about, which are jets. So, quarks and gluons appear experimentally as sprays of particles. I need a bigger piece of chalk. And whoops, that would have been good. The reason for that, right, is that you can't have a free quark or gluon, right? Because of the strong interaction, they actually need to hadronize almost immediately, and they end up hadronizing. So if you had a quark going here, almost instantaneously, you end up with this spray of particles. And that's the way that we can actually observe them. We can't see them by themselves. And now it gets a little bit different because actually we don't care about all those particles. I mean, we're not particularly interested, what hadron it is or things like that. What we really want to know is what were the properties of the originating quark or gluon. And so to do this, we use jet algorithms. And there are kind of 2 types. So these days, we basically just use one algorithm, but it's still useful to think about them. There is a geometric cluster algorithm, or set of algorithms. There's a bunch of them. And the basic idea, what you want to do is you want to think about your calorimeter, okay? And now you've got to think a little bit differently to tracking, because calorimeters are effectively 2D, right? You just get a measurement of energy in one of those towers. And so what you can kind of imagine is you take your cylinder of the calorimeter cells and you unfold it, right? So you're just unwrapping that layer of the whole cylinder. And then we're thinking about, how do we want to cluster together various different cells? And so jet algorithms, they don't have to be, but typically it's thinking in that sort of space that we would have. And so this would be phi, this one would be eta in terms of the space. And so for this geometric cluster algorithm, what we typically do is we cluster particles based on angular separation. Say again?
Angular at the vertex.
No, on the face of the calorimeter. Okay, so now we're looking on the face. Of course, you could project back and things like that later on. And because I'm in this eta phi space, right, I'm really in an angular space. And what that's trying to do, right, is it's saying when we produce this sort of spray of particles, they're typically close together, right? So we're clustering them based on angular separation because they'll generally be close together to do it. The second way are known as recombination cluster algorithms. And using a momentum-based metric. So in the former case, the metric we were using is we just wanted them to be close together. Here's thinking a little bit about, these particles that we have, because we're measuring the energy, of course, in the calorimeter. We're thinking we can actually use that information to determine which of the particles we want to combine together. Sort of classic one, which maybe you've heard of, is the KT algorithm. KT is just standing for momentum. And there, our metric would be Dij between two individual particles or energy deposits will be the minimum of KTi squared, KTj squared, delta Raj over R to do it. So this is the momentum, of your one particle or tower and the other to do it. And you're trying to loop over them, right, and identify which are the minima, which of these metrics to combine, and you keep iterating over this until you have normal combinations to combine to do it. For the theorists, I guess some people here work on QCD. Here's some nods. There's a lot of theoretical input that went into the development of these JET algorithms. In particular, one has to worry about things like infrared safety that we have. And so for quite a long time, there was kind of a, shall we say fight, but disagreement between theorists and experiments. Experimentalists like the geometric clustering algorithm because it gave you jets that looked intuitively what you thought a jet should look like. They were also easy to calibrate because they had regular shapes. However, it was not infrared safe, and the theorists wanted us to use the KT algorithm, which was great theoretically, but a pain to deal with experimentally. And so there was this little bit of, disagreement. But it actually turns out, I think this was in 2008 or so, the anti-KT algorithm, which is very, very similar here. You just change the metric to be KTi to the minus 2, KTj to the minus 2. This one satisfies everything theoretically that you want. It also ends up giving you cone-shaped jets, which was what the experimentalists want, which are easy to calibrate to do it. And so this algorithm is the one that we use almost exclusively at the LHC these days. Not entirely, like fat jets and big jets could be using different algorithms to do it, but this is the one we use. Yeah?
What's the I and J there?
Oh, so you're looping through your set of particles or towers or clusters, and it's just looking at all the different pairs to do it. And so you need to loop over them, right, to decide which are the pairs that you want to combine. And then once you've combined all the pairs or you reach a cutoff, then you would stop the algorithm to do it. Sorry, I didn't write out the full algorithm.
No worries. And then just to follow up, so for the KT algorithm, you're wanting to choose the smaller momentum, and for the anti-KT, you're wanting to choose the larger momentum. How
Well,
is
the
that given?
pair. It's the pair, right? You're choosing the pair which has the the minimum difference of 1 over the momentum to do it. As for why, I have to refer you to the paper for the exact details. I mean, I have to be frank, I've read that paper a number of times. I know what it does and how it, the jets it gives us, but I don't have a good intuitive explanation for why they end up being so circular. It ends up being like less sensitive to soft radiation, I think is sort of a loose answer, but not, you might want to look at the paper. It's by, I think, Kashiari et al., I think 2008 or so. But if you search for anti-KT, you'll find it. Yeah, you had a question? No?
I was referred to the paper.
Oh, exactly. Yeah.
Is there raw data available to test my own testing algorithm?
So this is an interesting thing that's going on at the LHC. There's been lots of pressure about whether the data should be fully open or not. There is some data that's public. For example, I think CMS has the best open data set that you can find on the open data portal. That being, and I think I've seen that a number of theorists have managed to, use this to do it. I have to say though, I've played a bit with some of the open data sets. Sometimes we don't really make them easy to use. So I guess they exist, but I give you a warning to do it. I mean, the truth is, and what I've tried to show you a little bit, is some of the complexity that kind of goes into this. And so it's actually hard to release a data set, right, with all the detail that you want to try your algorithm without having all this complexity that kind of comes out too. So that's a little bit of the true challenge that's sort of hiding behind it. Yeah?
Why? I mean, it's a complex task, sure, but that's kind of on the person that wants to do the analysis, right? Why do people not want this data released? I would think that this is scientific data that should be open to the public.
Well, the question is, at what level should it be open to the public, right? This is a bit the question. So obviously it is, like all the published results, et cetera, they are in all the HEP data, there's no discussion. The trouble is that we have a very complicated software that we have to apply, that will calibrate, will do various corrections and things like that. And I think some people's concerns are that you can find fake bumps in our data very easily if you don't treat it properly. And so I think some of the concern is then there'd be this whole big fuss, and we would be spending all our time, explaining why actually, no, that's just a dead tower in the calorimeter, or things like that. So this is a bit, there's a movement. I think it's going to become more open to do it. But there's quite a bit one has to think about when dealing with that. All right, any more questions? That was it for jets. Yeah.
Could you possibly, I mean, I've read some papers that kind of give weighting numbers to the tagging efficiency. Could you comment on B and C?
Sure. So the way that we actually do B and C is we take a jet, right, and we look for a secondary vertex within it. So it's really just combining these two together. And because, of course, what will happen is because you have a B quark, it's going to make both a jet and it's going to give you that secondary vertex. And then what we really do is we take all those tracks inside the jet, we feed them into some sort of deep neural network and the vertices, the tracks and the vertices, and we use that to discriminate between the different flavors to do it. A sort of typical number, like one of our main working points, would be a 70% efficiency for B jets. To do it, maybe 5% for C. And then the light rejection, that's very easy. It's like a factor of 1,000 or so to do it. And here, since we've been talking a little bit about differences between Atlas and CMS, here's where Atlas is better than CMS. And that's because of the pixels, because we have pixels with a smaller transverse size. And so we end up getting better resolution on the secondary vertices because of that choice.
And I guess it's an added follow-up. It's of interest to me, and I know a few others are interested here as well. What about top rates? I know those are harder.
What do you mean, like a top tagger?
Yeah.
So here I don't have like a great number for you, because typically what happens is this is something that's done by each individual analysis. So there are various different top taggers that people can write to do it. Whereas the B tagging, this is something that's at the reconstruction level that's for the whole experiment. Yeah, we'd have to look that up. There's lots of work. I think those are still at the sort of, people exploring them within analyses. think it'll be a few years before, everybody has a top tagger that they would use. Okay.
I'm not sure I understand.
Oh, shush. Siri has been listening closely to our discussion. She must have learned some interesting things. Say again? Yeah, I know. I was looking. There was like a whole long thing. She was really trying hard. Somehow, it always happens when I'm lecturing. Okay, now how long do we have? Not too bad. I want to actually try and put this all together by loosely talking through you an example of an analysis, okay? And the one I'm going to do is a complicated one, and that's on purpose, because I want to show you a little bit how all these things actually fit together. So it's going to be Higgs coupling to B quarks. So your tagging question was well timed, because, of course, we certainly rely on tagging here to do it. So first up, why are we doing this? Always a good question to ask, right? Analyses, take 2 to 3 years. Better have a good reason. Has the largest branching ratio. So if you want to check out all the decays and look at the total width, would be part of it. Of course, we have much better ways of doing the width. Secondly, we can probe Higgs coupling to fermions and quarks. Unfortunately, it turns out that despite nice big branching ratio, right, so we got plenty of events, good few million at the LHC, it's actually very difficult. And sort of the main reason for that is if you think, if you just have a Higgs boson, so let's do something like glue-glue fusion, producing a Higgs decaying to a pair of B quarks, all you have in your event are a B and a B bar, right? There's nothing else going on in that event. However, if you look generically at the LHC, the diject cross-section for BB bar is something like 10 to the 8 times larger to do it, okay? So that's going to be exceedingly difficult, right? If you're looking for a small signal in a background 10 to the 8 times larger, that's essentially impossible to do. There's another problem, which is that there isn't a trigger. So we do have triggers on jets at Atlas, right? No problem, we can do them. However, in order to keep the rate of it manageable, basically because of this large cross-section, they have much higher PT thresholds than you would want to have to find a Higgs. So we can't trigger on those 2 jets that come from the Higgs. Yeah?
Will the upgrade to the CMS trigger to include tracking help a lot with this?
It'll help a bit, not enough. I mean, what you can do, so this is going way beyond what I've said so far, is you can look for boosted Higgs, right? Then you end up getting higher PT jets, and then that would be something you could do to do it. But the inclusive one is still, I mean, the jets are soft. It's like 45 and 25. 25 GeV jet is super hard at the LHC. You have them in almost every event. And so the way that we actually do it is we use associated production with a vector boson. And so here, I'm just using the shorthand, where the V can be either a W or a Z boson. And so it's also called Higgs Strahling, where you radiate off a Higgs boson to do it. Now, why do I want to do that? Question I probably wrote badly.
No, it's fine. Just did you write something above that?
Oh, you want to see what's above? That I can fix. That's easy to fix. to do it. So why are we thinking about associated production? There are actually two reasons. So one, if you think about that vector boson, right, we can allow that to decay to leptons, right? So we could have W to L nu, or we could have Z to LL, and actually this one also works, which is Z to nu nu to do it. That gives us a trigger. Triggering on a single lepton, easy. We do that all the time. So this way we can select our events. So that's reason number one. Reason number two, backgrounds. This kills that dijet background, right? That one is not your main background anymore. And your main background becomes things like vector bosons plus jets or TT bar, which have much smaller cross sections. Yeah.
Would the zeta nu nu just be a missing energy?
Yeah. Yeah, this is a fun little detail. So we have missing energy triggers, which you can use. So you can basically sum up all the energy you see and look for the rest. It turns out that there's an amusing trick in Atlas that at level 1, so our sort of first level of the trigger, we can require a single muon, and missing energy effectively fires that muon trigger 100% because they don't do missing energy corrections in that step. So we actually end up with a 100% efficient trigger by chance, but using one that we shouldn't be using to do it. However, of course, the cross-section for that is much smaller, like 2.3 picobonds versus 49. So we lose a bunch of events. But we're happy to pay that price because we have much smaller background. Now, there are going to be 3 channels, actually, that we use. And it's going to be characterized by that decay of the vector boson. And so we actually call them very simply. This will be 0 lepton. This will be 1 lepton. And that will be 2 lepton. And by the way, I didn't tell you, but I cheated here. What I mean when I say lepton here, I'm not actually talking about all the leptons. I'm defining lepton to be either an electron or a muon. Okay, so first of all, they need to be a charged lepton that we're thinking about. And secondly, we don't use taus here because actually taus are way more messy objects, which I haven't talked about at all. They actually tend to look like a jet in our detector. And so here we want to use the clean electrons or muons, which we've talked about how you would actually go and reconstruct. And so that's why we do that distinction. But we don't have a good word for electron plus muon to do it. Other piece that we need are 2 B-jets. So here we would use that tagging algorithm that we were talking about. We would reconstruct 2 different jets, and we would require them to be B-tagged to do it. And that's the basic event selection that we're doing. And where appropriate, we would have some missing energy for the neutrinos to do it. But it's pretty much just like that that we want to do it. Yeah?
Did that cross-section number for this process encode the branching ratios to leptons of the vector bosons?
No. That was just the production process. Unless I messed up, because I was looking at the number now and I'm not completely happy with it, so I need to double check that number. I wonder if I mixed up 8 and 13 TV. I need to double check to do it. But you're right that the branching ratio to leptons gives you another big hit for both the W and the Z. You can think about actually doing them hadronically. However, then you run into the trigger issues again, because you end up you've got to look for jets, and they're not nearly as clean as a lepton. Leontal's giving me a good shake of his head. Oh, I know. But people have tried, hilariously. With hadronic? No. So this is the right way to do it. I was just saying, in principle, you could. But it's not going to give you much extra physics to do it. And then, once you've done that, your sort of main discriminating variable is called MBB, okay? which is your invariant mass of those two jets to do it. And you have a pretty annoying background. It's not really that wavy, but it's not a nice, smooth background. It's got a bunch of features in it. And of course, what you're looking for is a nice little peak there at 125 GV, right? That would be how your signal would show up. This picture is completely wrong. Signal still really small compared to the background. So it would be quite difficult to do it precisely in this way, and I'll tell you how we really do it in a sec. Yeah?
Are you only looking at on-shell processes, so like this kind of thing works out?
We are looking at on-shell for this to do it. So of course at the LHC we do look at off-shell, and that's how we use it to find the width. But there we do it in the very high resolution channels, like Higgs to gamma gamma, Higgs to ZZ, some of Higgs to WW. We need that mass. Without the mass, we would have no chance. Yeah. They are on shell because they come out of the production process. Yeah, you could, but I think they typically are on shell as well to do it. Yeah, they are. And in fact, for Z to LL, we often even cut on the mass of the Z. So there we sometimes can make an explicit requirement on that to do it. Yeah.
What is the y-axis?
Oh, sorry. Good question. I should always label both of them. This would just be the number of events that we'd have in data to do it. I don't want to put numbers. This is just meant to be a cartoon to do it. So it's really like taking all your events, right? Combining these pairs of jets and plotting the mass. This is the simplest way you could think about doing the analysis. By the way, the width of that peak, that depends on your jet resolution, right? Because you're combining two B jets, you get that energy from the calorimeter, and if you have poorly reconstructed jets or a poor calorimeter, this is going to be broader. If you have good in both of those, it's going to be narrower. And so that becomes an important factor for actually being able to see the signal here. However, what we really actually do is, of course, we use machine learning, because we use that everywhere in analyses these days. And we use that to extract signal from background. And I sort of mention in words, but I'll write it down. The main backgrounds are, no, I don't want a W. I want a V plus jets. In particular, when those are B jets, but other ones also contribute to do it. And also, particularly at 13 TeV, this becomes larger, TT bar production as well. There's a bit of multi-jet and a bit of diboson, which we should also talk about to do it. Diboson's kind of interesting. And there we're thinking about all the different combinations. So you could have like WZ, WW, and ZZ. And if you think back to the Higgs signal that we're talking about, this is exactly the same, except that we switched out the Higgs for a vector boson to do it. And so in particular, what you could think about is, say, we're looking at the WH production, and we're looking at WZ. If we have Z to BB, that's exactly the same as our Higgs, except it's going to have the mass of the Z. So if you look super, super carefully, you can actually get a second peak here. It actually can be larger than the Higgs peak itself to do it. And so that's diboson production, which will also be a background you need to worry about. Yeah?
I don't think this is Phaser's main purpose, but would Phaser be able to help make some of these measurements more precise, like the Z to nu?
No. The main reason is that Phaser isn't timed into Atlas, right? And so we can't correlate their results with ours in real time. Secondly, these aren't particularly forward. Most of the production here is fairly central, so there wouldn't be much acceptance for Phaser. Sorry, yeah.
What sorts of ML algorithms would they use? Just like classification for signal versus background?
Yeah, it's usually classification, and honestly, so far it's mostly been the simplest, which would be a BDT to do it. You can do better than that. Like we explored one time where we tried to use a multinomial, where you were trying to find like the signal and all the different backgrounds at the same time. But it became very complicated to combine it into the final discriminant. So we did it, but it was a huge amount of work we didn't anticipate to do it. Yeah, actually, speaking of that, for this ML, there are kind of three key variables. There is PTV, there's MBB, which I've talked about already, and then there is delta R BB. So this is just the angular separation between the B jet, Higgs mass, to do it. And then this one's kind of interesting. So this is the transverse momentum of the vector boson. It actually turns out that if you have a look at the PT, and it's the same for the Higgs or the vector boson, because if you look back to my Feynman diagram, well over there, they're essentially equal to each other, right? The Higgs and the vector boson have the same. And so we can measure it better. That's why we're looking at that one. But effectively, this is for VH, and this is for all the different backgrounds. And so the transverse momentum distribution of the Higgs is quite a bit harder than the different backgrounds. And so this is why you might have heard about boosted analyses. Going to higher boost can enhance your signal and decrease your background. You can also just use it as a variable in your machine learning to actually discriminate. And so these are the three that really matter the most, but we use like 20 as well. They add little bits and pieces to do it. Okay. One other thing I left out, because we have to keep making it more complicated, is something called categories. This is also something that we kind of do in many different analyses to do it. And the reason for it is that, roughly speaking, your sensitivity, i.e. how accurate a measurement or search you can do, depends on S over square root B. Right? More or less. You can make corrections, you can make that better, etc. And so what that means, right, is if you take all your events together, you'll be combining events which have high signal and low background with those which have low signal and high background. So your total will be worse. And so if you can actually chop it up instead, in some way, into events which have high signal or high significance and low significance, you will improve the overall sensitivity of your analysis to do it. Yeah?
Is there some reason to put that B in a square root?
Yes. That's how, I mean, if you actually go through the calculation of the significance, roughly speaking, it looks like that. I need to do a correction for the uncertainty on the background, which I didn't do to do it. So
this is just some variable defined in this way?
It's pretty much the significance. It's the statistical significance of the analysis. But there are various regions where it doesn't work quite perfectly. That's why I'm saying roughly to do it. It's the thing you want to be as good as possible. And so what that means, what we do, is we separate into categories according to S and B to do it. So you got to imagine, right, we take this whole big phase space, right, all those events, we chop them up into various different categories. Give an example. PTV is one of a good way of doing it. So what we typically do is we actually define 3 different regions in PTV. And those are 3 of the categories that we would use. Also, another way we do the categories is, you know, how like a B jet is it? How many B tags do we have? This is another way that we separate them. And so all in all, it's like order 20-ish categories that we would have to there. Yeah?
Is that the same as splitting into different signal regions?
Yes, except they're not all going to be signal regions. It's the same idea, though. In fact, some of these are also used as control regions. And formally, by the way, there's no difference between signal and control regions. It's just a way we like to talk about it. Statistically, we're going to treat them exactly the same. However, a signal region is designed to extract a signal. A control region is designed to constrain a background. So unfortunately, we're trying to find a Higgs boson. We don't care right now too much about, V plus jets or TT bar, but we depend on the uncertainty on them. And so what we do with control regions is we try to make one that would be very pure in TT bar, and that way we can actually figure out our background from the data itself for the uncertainty. And so that's what we use them for there. Okay. We're getting there. So then we train whatever we're going to use. So let's say we're using a BDT, for example. And again, you get some sort of curve here that we would have. However, if we've trained it well, this would be our background, and this would be our signal. And so here we're just doing classification. We're training our signal to be separate from the background. And so this is our most sensitive region we'd have. And we do that in each of our different categories. We train one. Yeah?
When we're trying to when we go through some analysis of some theory and we try to push it into the lighter stuff, we generally just estimate our background as root n. Are there places where that's just wildly off as non-Gaussian?
Yes. Systematic uncertainties.
Okay.
Right?
I guess those are always there.
Yeah, and in the end, unfortunately, for this sort of analysis and for many, they can become important. But the thing is, right, there are systematic uncertainties from theory, these you know. Then there are systematic uncertainties from all these different experimental effects. But these you can actually know, right? So B jets will have a certain uncertainty, jets will have a certain one. And so one can actually add that information in to improve it, to do it. Then the final step is we use a likelihood fit. In fact, it's called a profile likelihood fit. And this is a technique we use for pretty much every single Higgs analysis at the LHC. A bit short of time, so I'm going to leave out all the details of the equations. But essentially, what we have is we have a likelihood, which is a function of a parameter mu and a set of parameters theta. And mu is actually going to be the strength of the signal we're interested in. So here we're trying to find Higgs to be B. So mu is going to be our signal strength with respect to the standard model prediction. So if we find that mu equals 1, we probably did our analysis correctly, but the standard model is true. If we find mu not equal to 1, that would be really exciting. It means it would either be a lower cross-section or a higher cross-section. It's kind of a proxy for a cross-section to do it. But the reason why this word profile comes in are these thetas, okay? These are actually how we treat all our different systematic uncertainties in the analysis. So for example, right, on our electron, we'll have an uncertainty on the efficiency. So we'll have a theta parameter for that uncertainty. Certainty on the B tagging, we have a theta parameter. On our theory predictions, etc. And so you have order 200 of these different thetas in it. Now what actually happens, once you've defined this likelihood, you will actually run over all your different histograms that you have in all your categories, and we'll try to minimize our likelihood here. But what's interesting is that our thetas don't stay fixed. In case our data is more accurate than our uncertainties, we allow our data to actually constrain them to do it. And so this could actually reduce the impact of uncertainties. And in fact, in many Higgs analyses, this constraint is how we're actually able to do them. So it's an extremely important step that we do it. It's also very dangerous. If you set up your fit wrong, you can get garbage out of a likelihood fit by constraining things in artificial ways that don't make sense to do it. So it is something that's really important to pay attention to when you look in these analyses to understand if it makes sense or not. Questions? All right. So, I used the wrong board. Doesn't matter. So just to conclude, so we had observation here in August 2018. And there's actually a kind of a funny story here about it, because at the LHC, there is a deal between the experiments that if anyone makes a discovery, you're required to notify the other experiment 1 week before you release it, okay? As for why, there's a long history at CERN about why that might be the case. You might want to look into observation of W's and Z's back in the day to do it, but this is the rule. And the way that in practical terms it works is, one spokesperson goes to the DG, then they talk to the other spokesperson. You often provide them with a plot, often without labels. And so we've had that in the past. So once we were given a plot by CMS, an unlabeled plot, and we were trying to figure out what the plot was for a week, and we failed to do it. That wasn't for this. So what happened here is back in a couple weeks before ICHEP, in August 2018, CMS notified Atlas that they were going to have Higgs to BB observation to do it. Now on the Atlas side, we'd been working on our analysis. It was almost finished, but it was still blinded to do it. So we do these blind analyses to try and avoid bias. Of course, when that happened, a spokesperson came to talk to the conveners and said, can we actually get this done, in a few weeks' time? And, major, we can't, whatever. In the end, okay, fine, we're going to do it. So everyone worked like mad for a few days and blinded the analysis, looked at it, had observation, everything looked great. Fantastic. Then CMS comes back to Atlas. They said, actually, we're not going to do this. Can you guys wait to do it? Because it turns out that they had told us before they unblinded. They did unblind, they found some issue in the analysis and didn't want to actually make it public to do it. At this point, Atlas put out their result for ICHEP and got to do the first observation for Higgs to BB to do it. So, yep, that's how things can actually work out a bit in practice. But just to give you an idea kind of where we're at, so sort of recent measurement of mu, and I wonder if I have a typo here. I suspect I do. Yeah, I'll give you this one. Was 1.01 plus minus 0.2 of statistical uncertainty plus minus, well, actually not plus minus, we're going to be very precise, plus 0.16 minus 0.15 systematic uncertainty. So this is not from the observation. This is sort of one of the most recent things. And first of all, you can see we agree quite nicely with standard model. That's just how, unfortunately, all our Higgs analyses look for the moment to do it. The statistical uncertainty is 12%. Systematic is about 15%. And if you look at that naively, you might say, it's systematically limited, right? So it means you add more data, it's not going to actually get better. Actually, not really true, because some of the things inside our systematics are things like normalizations on our backgrounds, uncertainties on some of our efficiencies, which we will be able to measure more accurately with more data. So we've always had a little bit of trouble with this. One needs to sort of treat that with caution. Now, the most important systematics, just to conclude, number one is the signal model. And so this is a theoretical uncertainty, basically on the modeling of the signal. So that's something you guys can help with to reduce for the future. And that's something like, I think, 0.09. Number two is very sad. It is Monte Carlo statistics, which is something like 0.07. What that means is that we're not able to simulate enough data to use for the analysis such that we're sensitive to the statistical fluctuations. So that goes back to some of the things I was saying, how fast you can simulate things can really matter. And here it impacts the size of our uncertainty. After that, we have various V plus jet normalizations. So this is, how accurately do we know the number we have? There's about 0.6. And finally, it's the B tagging. So the first kind of real experimental uncertainty comes in again, and this is 0.06 as well. So that's it. I wanted to give you sort of quick overview about how we take all these things we've been looking at and try and put them all together into an analysis, and also show you a little bit about kind of what's hard inside an analysis, right? Not just showing you the pretty result, which is what we show at the conference, to do it. So yeah, any last questions? Or does everyone need coffee? I think everyone needs coffee.